In the last lecture, we talked about two main types of questions, x to area and area to x. And this was the workflow that we used to solve all of those questions. Now, in the last section, I was careful to include the words normally distributed in every single question. And the reason is because p-norm, q-norm, they both have the word norm in them, only work if your distribution is normally distributed. In other words, these only apply when your distribution looks like this. The picture that we drew on every single question. Now, the question is, what do you do when your distribution does not look like that? Because in Unit 1, we've seen lots of histograms that don't look like that. We've seen histograms that were skewed left, histograms that were skewed right, and histograms that have multiple peaks. What do you do in those situations? To answer that question, I need to introduce a couple of new ideas. The first idea, the setup is this. So suppose we have a population that has a certain mean and a certain standard deviation. To make this concrete, let's say that the population I care about here is the population of all college students, and what I care about is their age. So mu here is the average age of all college students. Sigma is the standard deviation of the ages of all college students. And what I'm going to do here is I'm going to take a sample. Take a sample of size n, and then I'm going to take the average. And the average is x bar. So in our example here, pretend I'm taking a sample of 30 college students, and then I'll find their average age. Now, these two symbols, x bar and mu, they both stand for average. They both stand for mean. X bar is the average of just those 30 students in my sample. Mu is the average of all college students. All right, so now let me show you a demonstration. All right, so picture at the top here represents the population. So the population we're talking about here is the population of all college students. The numbers at the bottom, these represent the ages of college students. And what I care about here is the mean, which is 25 in this case, and the standard deviation, which is 5. And what I'm going to do here is I'm going to take a sample of size 1. So in other words, I'm going to take one random student and then record their age. So that's one random student, and then I record their age at the bottom here. Another random student, and then record their age. Another random student, and record their age. And then I'm going to repeat this process many, many times. And look at the picture that I get. Notice that the picture looks roughly the same as the original. The mean of the bottom picture, 25.0301, roughly the same as the original, which was 25. Standard deviation, 4.986, roughly the same as the original, which was 5. That's picking one random student, okay? Everything stayed the same. What happens now if I increase the sample size to 5? What I'm doing here is now picking 5 random students, find their average age, and then record at the bottom. Taking another 5 random student, find their average age, and record. Take another 5 random students, find their average age, and record. And then repeat this many, many times. Notice what happens. The picture no longer looks exactly the same. It got narrower, right? The mean, 25.0043, roughly the same as the original, 25. The standard deviation, 2.2496. That did change, right? It got smaller. The original was 5. Now let me increase the sample size to 10. What this means is I'm going to pick 10 random students, find their average age, and then record. Pick another 10 random students, find their average age, and record. And then repeat this process many, many times. Notice what happens. The mean, 24.9973, stayed roughly the same as the original, which was 25. Standard deviation got even smaller, 1.5825. With 5 people, it was around 2 something, and now with 10 people, it went down to 1.5825. Let's record what we just saw. When we take a sample size n, so when we pick n random people, find their average, and then record the average, these averages have mean. I'm using the notation x, mu x bar to distinguish between the bottom picture and the top picture. So the top picture is the population, the bottom picture is the x bar. So when I say mu x bar, I'm referring to the bottom picture. When I say regular mu, I'm referring to the top picture. So when we look at the bottom picture, the mean we said stayed the same. So the mean is the original mean. Standard deviation of the bottom picture, we saw that as the sample size gets bigger, the standard deviation actually gets smaller. Mathematically, what's actually happening is we're dividing the original standard deviation by square root of n. So as the sample size n gets bigger, you're dividing by a bigger number, which is overall going to give you a smaller number. Which is why the picture gets narrower, right? Because standard deviation is a measure of how spread out your data is. So if your standard deviation is smaller, your picture overall is going to be narrower. Right, so now I'm ready to answer the question that I had at the beginning of the lecture, which was, what do you do when your distribution is not normally distributed? So here, I changed the original distribution of the original population so that it's no longer normal. Now it's heavily skewed to the right. And we're going to do the same thing. I'm going to start off by taking a sample of size 1. And based on what we just saw, taking a sample of size 1 shouldn't change the picture. So I expect the picture at the bottom to look the same. And it does. Now, what happens now when I increase the sample size? I'm going to increase the sample size to 5. Okay, we expect the mean to stay the same, and we expect the standard deviation to decrease, but look at what happens to the picture. The picture changed. It looks less skewed to the right now. It may be still slightly skewed to the right, but it's definitely less skewed to the right now. Now look at what happens when I increase the sample size even further, to 30. Now it looks no longer skewed at all. Now it looks very much like a normal distribution. Let me take this one step further. So let me mess up this distribution even more. That distribution is definitely not normally distributed. If I take a sample of size 1, okay, we expect the picture to be the same. And it is. Now, if I increase the sample size to 30, what do you think happens? That looks like a very normally distributed picture, okay? And that's the most important idea in all of statistics, right? This is the idea that makes everything work. So regardless of what the original population looks like, if you pick a sample size big enough, in this case I'm picking 30, the picture at the bottom is always going to look like a normal distribution, no matter what the original picture looks like. Let's write down what we just saw. So what we just saw was, if you pick a sample size big enough, and big enough is going to mean a sample size that's bigger than 30, then the averages, x bar, right? This is referring to the bottom picture. Then the bottom picture will be approximately normal. and it will have a mean that's equal to the original mean, and it will have a standard deviation that's going to be equal to the original standard deviation divided by square root of n. So if you pick a sample size big enough, which is bigger than 30, then for sure the picture at the bottom, the averages x bar, will be approximately normal, and it will have mean and standard deviation these. So I think this is the most important theorem in all statistics. And the reason why is it answers our original question of how do you deal with distributions that don't look like this? And the answer is, as long as you pick a sample size big enough and look at the averages, the distribution will look like this, which means we can now use p norm and q norm. But more importantly, we're taking samples so that we can learn about the population, right? Which most of the time we don't know anything about. In other words, we don't actually know what the original population looks like, what the distribution looks like. And what this is saying is that who cares, right? Who cares that you don't know what the original distribution looks like? Because as long as you pick a sample size big enough, this will be the picture. And that's why this picture and this theorem are so important in statistics. Now we're ready to answer some questions. Same process as in the previous lecture. Same two main types of questions, x to area and area to x. Same workflow. The only thing that's new is what's inside of these two boxes, which is actually the same box. So what's inside of these boxes is saying the mean stays the same, so that you don't have to worry about. The standard deviation, though, you do have to worry about. So if you're taking a sample of size n, what this is saying is that you have to adjust the standard deviation by dividing it by square root of n. And that's the only thing that's new in this section. Example 1. The mean cholesterol level for US adults is 202 with a standard deviation of 41. If a random sample of 110 adults is chosen, what's the probability that their mean cholesterol level is between 190 and 200? The first thing I'm going to do, just like in the previous lecture, is draw my picture and put the mean in the middle. My mean here is 202. And then I'm going to make a note to myself of what this 202 represents. So this 202 represents the cholesterol level. And then the next thing I need to do is decide whether this is an x to area or an area to x. It says, what is the probability? And remember, whenever I say probability, percent, or proportion, you should think area. It says, what is the probability? What is the area? We're looking for area as a final answer. This would have to be an x to area problem because you want to end up with an area. And now let me put the rest of the numbers on this picture. 202 is the mean. We put it already on a picture. 41 is standard deviation. You don't put that on the picture. 110, this is the sample size. We're going to worry about that a little bit later. 190 and 200. Okay, these are cholesterol levels, right? So these are actually my x's. These should go on the x-axis. 190 and 200, these are actually both on the left side here. Okay, I want between, so I'm looking for the area between. So this is an x to area, and I'm looking for the area between. Now, the one extra step here before I go and do my workflow is I'm going to write down my mean and my standard deviation. So my mean here is the 202. The standard deviation, okay, if I'm given a sample size, which I am here, I have to adjust it by dividing by square root of n. So I do need to adjust this 41 by dividing it by square root of the sample size, which is 110. Okay, so on my calculator, 41 on top, on the bottom square root of 110. And then round this to 3 decimal places. So it's 3.909. And that's the standard deviation that you're going to be using for the rest of this problem. Not 41, 3.909. Now, we said it was x to area. So x to area, the first thing we need to do is the z-score. And I have two x's here, so I need to do two z-scores. The first one for the 190 is going to be 190 minus the mean, which is 202, divided by the standard deviation, which we said was this 3.909. Right, so I'll do that a little bit later. For my second x, which is the 200, minus the mean, which is 202, divided by the standard deviation, 3.909. Okay, so let's do both of these on the calculator. First one, 190 minus 202 on top, divided by 3.909, negative 3. Rounded to 3 decimal places here is 0.70. Okay, the other one on top, 200 minus 202 divided by 3.909, negative 0.512. Okay, we just did z-score formula for both my x's. Next step is to do p-norm both of my z's. So we're going to p-norm this negative 3.070, and then we're going to p-norm negative 0.512. And this you do in R. So in R, p-norm negative 3.070. That's 0.001. Okay, p-norm negative 0.512. Rounded to 3 decimal places here, 0.304. Okay, now the way p-norm works, remember, is p-norm takes a z, it spits out left area. So both of these are left areas. If I want the area between, what do you do with these two areas? Subtract. Okay, so we're going to go the bigger one minus the smaller one, so 0.304 minus 0.001. Okay, and that is, I know I don't need a calculator for this, but let's just use it for fun. 0.303. Example 2. Typing speed is approximately normal with a mean speed of 45 words per minute and a standard deviation of 10 words per minute. What's the probability that a random sample of 12 people have mean typing speed of more than 40 words per minute? Same as before, first thing I'll do is draw my picture and put the mean in the middle. Our mean here is 45. And then to keep track of what's on my x-axis, this 45 was words per minute, or is typing speed. Okay. Next thing I need to do is figure out whether this is an x to area or an area to x problem. It says, what is the probability? Probability we said was area. So what is the area again? I'm looking for area as my final answer, so this would have to be an x to area problem if I want to end up with an area. So this is another x to area. And then to draw the rest of my picture, your picture here is going to be shaded in between, shaded to the right, or shaded to the left. Okay, so 45 was the mean, we got that. Standard deviation, we'll deal with that later. 12. That's the sample size. We'll deal with that later also. I do need to put this 40 on my picture. So 40 here is a words per minute. That's a typing speed. So that should go on the x-axis. So this is an x. 40 is here. Question is it shaded left or shaded to the right? It says more than 40, right? More than 40 would be on the right side. So this is shaded to the right. And then the extra step compared to the last section is I need to write down my mean and my standard deviation. My mean stays the same, that I don't need to worry about. My standard deviation I do need to worry about. Okay, I am given the sample size, 12. So I do need to adjust my standard deviation by dividing by square root of 12. So my standard deviation that I'm going to use here is going to be the original standard deviation, which is 10, divided by square root of the sample size, which is 12. Okay, so standard deviation I should be using is 10 over square root of 12. Rounded to 3 decimal places, this is 2.887. And then now for my workflow. So this is x to area. X to area, I should do x to area, my z-score formula first. So first thing I need to do is the z. X minus the mean, so our x is the 40, minus the mean, which is the 45, over the standard deviation, which is a 2.887, not the 45, I mean not the 10, but the new one, which is 2.887. Okay, on my calculator, up top, 40 minus 45. On the bottom, 2.887. -1.732. Negative 1.732. Okay. We just did the z-score. Next up is p-norm. So we're going to p-norm negative 1.732. Okay, 0.042. Is that my answer? Based on my picture, that's a kind of a big area, right? And this is only 0.042 is 4.2%. That can't be right. Right? I'm expecting a big percentage here. And the reason why this is wrong, right, is remember, p-norm, the way p-norm works is you feed it a z, it always spits out the left area. If you're looking for a left area, then that's your answer, but that's not what we're looking for. I want the right area to the right. So to get the right area, you have to do a 1 minus, right? Because this 0.042 is this unshaded part. To get the other side, you do 1 minus. Okay, so our final answer, 1 minus 0.042. 0.958. Okay, 95.8%, that's more likely. Example 3. The mean distance that commuters in the US travel each day to work is 16 miles. The standard deviation is 8 miles. If 75 commuters is chosen, there's a 94% probability that the mean commute distance is between what two values? First thing I'll do is draw the picture and put the mean in the middle. Our mean here is 16. And then to remind myself, this 16 stands for miles, or commute distance. The next thing I need to do is decide whether this is an x to area or an area to x. Notice that I'm giving you a percent here, right? I'm giving you, and percent is area, so I'm giving you an area to start with, which means this would have to be an area to x problem if I'm starting you off with an area. This is an area to x. And then to draw the rest of my picture, 16 is the mean, we got that already. 8 is the standard deviation, we'll deal with that later. 75, that's how many people, how many commuters, that's the sample size, we'll deal with that later. I do need to put the 94% on my picture. Okay, so that's an area, and I want two values, right? I want two commute distances, so this is I want two x's with an area in the middle that is 94%, which is 0.94 as a decimal. So I'm looking for two x's that have 94.94 area in the middle. Now, let's write down the mean and write down the standard deviation. our mean is 16. Standard deviation, okay, we do have to adjust here, right? Standard deviation should be 8 divided by square root of the sample size, which is how many people we're talking about here. 75 people. All right, so my standard deviation that I should be using for the rest of my problem is going to be 8 on top, square root of 75 on the bottom. 0.924. Okay, so remember, round each intermediate step to 3 decimal places. All right, this is an area to x problem. First thing I need to do is Q-norm the left area. Okay, so we'll Q-norm the left area. What is the left area? Is the left area 0.94? No, right? 0.94 is the area in the middle. I want this left unshaded part here. Okay, so what I need to do here is 1 minus 0.94. Right, so if I have a shaded area and I do 1 minus, that gives me the unshaded part. So 1 minus 0.94 is 0.06. Okay, that's the unshaded part, which is actually the left and the right together. If I just want the left side, what do? You divide it by 2. Okay, so 0.06 divided by 2 is 0.03. Okay, and that's the left unshaded part, which is what I want to feed into R. Okay, so now in R, Q norm 0.03. Okay, this gets me from area to Z. So what R spits out is a Z. So this is a Z of negative 1.88. Rounded to 3, this is 881. Now, I want 2 x's as my final answer, which means I need 2 z's here. Okay, so that's one of them. The other one, so negative 1.881 is the one that goes with the left one. The one that goes with the right one is just going to be the positive version of this. So the one on the right is 1.881 positive. Now that I have my 2 z's, to go from z to x, use this formula for x. So x equals the mean plus z times the standard deviation. Okay, the mean was 16 plus z, negative 1.881, times the standard deviation. And standard deviation, remember, we're not going to be using the 8. We use the adjusted one, which is 0.924. So 16 plus, parentheses, negative 1.881 times 0.924. 14.262. That's one of them. For the other one, same thing. X equals the mean, which is 16, plus the z, this time is the positive 1.881, times the standard deviation, which is the 0.924. Okay, and this one's going to be 16 plus positive 1.881 times 0.924. 16.045. Okay, so those are my 2 x's. It does match the picture, so I think we're good. Example 4. The mean hourly wage of people in California is $14 with standard deviation 8. A pollster draws a sample of 60 people to interview. There's a 32% probability that the mean hourly wage of people in the sample is greater than what value? First thing I need to do is draw my picture. Put the mean in the middle. Our mean here is the 14. Okay, so this 14, to remind myself later on, this 14 is what? It's dollars. It's the hourly wage. And then I need to decide whether this is a x to area or an area to x. I'm giving you a percent here. That means I'm giving you the area. So I'm starting you off with area. So this would have to be area to x, because that's the one that starts off with area. Okay, so this is area to x. And then to draw the rest of my picture, 14 I got already. Standard deviation, we worry about that later. 60, that's a 60 people, right? That's a sample size. We worry about that later. I do need to put the 32% on my picture. So we have to decide what type of picture is this? Is this to the left, to the right, or between? So 32% probability that the mean hourly wage of people in the sample is greater than what value? So greater than, that tells me that this 32% is to the right, okay? 32% to the right, that would go somewhere over here. And that 32% is an area, so that's up here. So I'm looking for what x would have a area of 0.32 to the right. So what hourly wage would have a 0.32 area to the right. Next up, let's write down my mean. My mean is 14. And let's write down my standard deviation. Standard deviation is going to be 8 divided by square root of my sample size. So how many people are we talking about here? 60 people. So 8 divided by square root of 60. So my standard deviation is going to be 8 on top, square root of 60 on the bottom. 1.033. Okay, that's rounded to 3 decimal places. And then now my workflow. So my workflow is this, we said it was area to x. Area to x, first thing I need to do is Q norm, left area. Left area goes here. Is 0.32 my left area? No, right? 0.32 is the shaded part, which is area to the right. I want this unshaded part. So if you want the unshaded part, if you want the other side, do 1 minus. So 1 minus 0.32. And 1 minus 0.32 is 0.68. All right, so 0.68. So that goes here. So we're going to Q norm 0.68. And we get 0.468. 0.468. And what is that? So Q norm takes you from area to Z. So that's a Z. So our Z here is 0.468. And then finally, to get from Z to X, use the X formula. So that's X equals the mean, which is 14, plus the Z, which is the 0.468, times the standard deviation, 1.033. All right, so X here is 14 plus parentheses 0.468 times 1.033. 14.483. Example 5. Credit scores are normally distributed with a mean of 592 and a standard deviation of 106. What is the credit score of someone who is at the 92nd percentile? All right, draw my picture. Put our mean in the middle. Our mean here is 592. And then label this x-axis. This 592 stands for the credit score. So these are credit scores on the x-axis. And then decide whether this is an x to area or an area to x problem. Now, 92nd percentile, right, means 92% of the data is below. So 92% below. I'm giving you a percent. I'm giving you 92%. So I'm giving you a area, which means this would have to be an area to x problem if I'm giving you area to start. So this is area to x. And to draw the rest of my picture, right? 592 is already on my picture. 106 is the standard deviation. We don't put that on the picture. 92%, that's an area. So I want 92% to the left, right? Below means to left. So I want 92% to the left, which would have to be somewhere over here and shaded to the left. Okay, so 0.92 is the area, which means I'm looking for this x that would have 0.92 to the left. Okay, let's write down the mean and standard deviation. The mean here is 592. Standard deviation 106. What's our sample size? It's not there, right? 592 we use, 106 we used already, 92% we used already. There's no sample size. So if you're not given a sample size, you're going to assume that's one person. Okay? In other words, 106 divided by square root of 1 is just going to be 106. In other words, you're going to use the original standard deviation. If you're not given a sample size, you're going to use the original standard deviation. All right. So this we said was area to x. Area to x. First thing we need to do is Q norm left area. .92, is that the left area? Yes, it is, right? The shade to left is 0.92. So I don't have to do any adjustments here. It's just 0.92. Okay, so in R, 0.92, Q norm 0.92. Okay, Q norm should get me from area to a Z, so that's a Z. So Z here is 1.405. And then from Z to X, we'll use the formula for X. So X equals the mean, which is 592, plus the Z, which is 1.405, times the standard deviation, which is this original 106. And our answer, 592 plus parentheses 1.405 times 106. 740.93. Okay, so for all of these questions, we've been drawing the same picture and we've been using Q norm, P norm blindly, right? We didn't really question whether we were allowed to do it. So let's now answer that question, right? When are we allowed to use a normal distribution? In other words, when are we allowed to draw this normal distribution picture and use P norm, Q norm? And that's answered by the central limit theorem that we talked about on the front page, is that if your sample size is big enough, yes, you can use the normal distribution. If your sample size is big enough, bigger than 30, then no questions asked, you can use it. If your sample size is small, which is less than or equal to 30, then you will need to know that the original population is normal in order to use the normal distribution. Then you need to know that the original population is normal. In order to use the normal distribution. Let's go through some of these examples and decide, are we allowed to use the normal distribution or are we not? Part A, a sample size of 45 will be drawn from a population. So I don't need to read anything else. I see 45. 45 is bigger than 30. So for sure, no questions asked. Yes, you can use the normal distribution. So this is a for sure yes. Part B, a sample of size 8. Okay, so this is now a small sample size. So I do need to see normal population somewhere else in the problem. A sample of size 8 will be drawn from a normal population. I do see it. With mean this and standard deviation this. Is it appropriate to use the normal distribution? Yes, right? Small sample size. I do know that the original population is normal. So yes, I can use the normal distribution. In other words, I can draw this picture and I can use P norm, Q norm. Part C, a sample of size 24. Okay, this is now a small sample size again. So I do need to see the words normal population somewhere else in the problem. Will be drawn from a population with mean 35 and standard deviation 1.2. Okay, I didn't see the word normal anywhere else in the problem, so I can't. So this is a no. And in reality, if you encounter this situation, the way you fix that is pick more people, right? As long as you're over 30, then you can use normal distribution. Pick more people. All right, that's it for today. Have a great day. See you in the next one.